my lecture today. Of course, today we're going to continue with the jointly distributed random variable that we started on Monday. So we're going to be focusing on the expectation and variance of jointly distributed random variables. Of course, that is not surprising when you take a look at, before when we focus on one measurement at a time, okay, from a given probability function, whether discrete or continuous, where we're able to figure out the expectation of a random variable as well as its variance. So we can also do the same when we are focusing on jointly distributed random variable. Of course, I told you yesterday, the jointly distributed random variable, we know we're talking about situation where we got more than one observable measurement. Okay, those events are occurring simultaneously. And of course, the jointly distributed function will enable us to be able to investigate some, uh, basic statistical inference, like looking at the relationship between variables and stuff like that. But like I said, the focus today will be on getting the average and the variance. Of course, that is typical of what happened in a stochastic world where there's variation. We normally want to figure out what is going to be the mean and what is going to be the variance. But let me tell you this: when we want to focus on the mean, focus on the variance, we're going to have different two types of means, and we have two types of variances. Okay, that's applicable to a jointly distributed random variable. Okay, the first one is going to be unconditional mean, which is just going to be expected value of x, expected value of y. Then we're also going to have conditional mean, okay, which is going to be expected value of x, expected value of x given y, or the expected value of y given x. And of course, uh, we also going to have a conditional variance. This is a conditional variance for this, and we're also going to have conditional variance for that as well. So these are conditional means. Okay, conditional means, and these are conditional variances. Okay, conditional variances. Okay, so we can only have stuff like this, in a jointly, related, jointly distributed function. Okay, so the further examples we're going to have today on the joint probability distribution, we focus on on all of this. Okay, the unconditional one is this guy. Of course, if I want to find the expected value of x, I also need the variance of x. If I want to find the expected value of y, I also need the variance of y. Okay, so these are unconditional. Okay, these are unconditional. Okay, why these are conditional? Okay, we're basically going to have stuff like this, in a jointly distributed function. Now, I want to walk you back into what I started on Monday. Okay, like having a recap on a situation where the joint function is discrete in nature, right? So take a look at what I got. The probability of x and y, looking at probability of the joint occurrence of two events at the same time, which is actually what you're seeing. And of course, that have to satisfy the fact that it has to be non-negative. And at the same time, okay, when you sum that, it has to be equal to 1. And I also show you yesterday that from the joint, we can actually find the marginal. Okay, you know what you're seeing now? You're seeing the f of x, right? Give me 1 second. you're actually seeing this guy now, right? The P of X, okay, which means I'm actually need to sum. If I'm interested in a function of X, I'm basically going to sum, okay, the joint, okay, over the range of the variable I'm not interested in. I'm also going to do the same to Y. So these are called, you know, marginal probability. But let me tell you this. What do we get from marginal probability? What do I get from P of S? What do I get from P of Y? I can find my unconditional means and my unconditional variances. For instance, I basically want to find the expected value of X. If I want to find the expected value of X, I need P of X. If I want to find the expected value of Y, I need P of Y. Does that make sense? Okay, so that's exactly what I mean there. Okay, now if you take a look at C, the mean of a function of, you have functions that is jointly distributed. You have more than one variable, and basically want to figure out the mean. You can say the formula now. You want to figure out the mean. The number of summation you're going to have depend on the number of variables. We got two summation now. Let's take a look at if you take a look at this guy now that I'm trying to circle, right? Okay, you're basically going to see that is a formula to figure out the expectation of, you know, of that particular function h of xy. Okay, now I need you to pay attention to what I just circled now. The h of xy is another function. It's not a probability function. The probability function is the p of xy. The P of xy is the joint probability function. But you know what? If I want to find the expectation, then I need to find the expectation of a random variable or expectation of a linear combination of a random variable. If you see h of xy, that is basically a linear combination of x and y. Okay, now if that is basically going to be the case now, okay, now if you take a look at the I said also p of xy lies in A, okay, automatically we are actually going to be considering, because we're considering two different type of measurement, okay, then the state space of x and the state space of y basically going to be coming from real number. Now I'm going to show you another example. Now I showed you some example yesterday about the discrete, about the continuous. It's another example. Anytime you see a contingency table like this, okay, what should come to your mind, you are actually working with a joint PMF. That's for discrete. The discrete, we normally have a situation where the variables, we have levels. The levels of x, y here is 3, 0, 1, 2. The levels of x is 6, 0 to 5. And as you can see, the values that you see 0.025 all the way to 0.020, they are actually the possible pair of the joint probability when you consider a level in x and a level in y. And we could have some questions. Take a look at the first question. Find the probability of x equal to y. Okay. Now, if you want to find the probability of x equal to y, then this is what you're trying to do. 0, 0, 0, 0, 1, 1, 2, 2. If you go back into the table, of course, there can never be 3, 3, because the state space of y terminates at 2. Does that make sense? So all what I'm just going to do is to go back to the contingency table and try to read out, okay, what I mean. Okay, take a look at this guy now. Give me 1 second. So if you take a look at this guy now, as an example, which correspond to 0 here and 0 here. Okay, and you're going to go for the one for 1, 1, for 2, 2. Okay, in the hand, you've already obtained that. The answer to that question, the probability where x equal to y, is basically 0.105. Is there anybody want any clarification on that? Okay. Those of you online, can you see confirm? If you can see, hear me clearly. Those of you online.
Yep, we're able to see and hear clearly.
Okay, thank you so much. Now, the next question here is a B. It's a find the marginal distribution of x and y. Okay, finding the marginal distribution of x. Okay, now there are six values, possible values in x. So I actually need to find when x equal to 0, when x equal to 1, when x equal to 2, all the way to when x equal to 5. When x equal to 0, I'm actually going to sum it over the range of the variable I'm not interested in. I'm not interested in y. When I'm focusing on s, I'm not interested in y. Okay, so that is why take a look at number B. The way I figured that number B out now, you're actually going to construct a table. If you basically want to figure out a function of x or a function of y from a given contingency table. Okay, take a look at what I have now. How do I come out with 0.05? Okay, I actually come out with the 0.05. Okay, so what I actually did, okay, if you take a look at this guy now, okay, that is basically going to give me the probability of s equal to 0. All what I'm just going to do is to add it up, which means I'm adding, over the range of y that I'm not interested in. I'm going to do it for when s equal to 1 all the way to s equal to 5. Any question? I think so. And that was how, when you do all of that, you're basically going to have that particular table. But let me tell you this. I remember when I was in college, before I turn in my exam script, I normally check. How do I check? If I add all the probability here together, it must give me 1 if I'm right. Okay? So when you add the 0.05 to 0.1 to 0.25 to 0.3, 2.1, you should have 1. The moment you don't have 1, then something is missing. Okay. Now, do you know that if I now ask you to find the expected value of x, the expected value of x here, then I need x and the probability of x. You remember what we normally do, right? If I want to find the expected value of x, I'm actually, and this is a discrete, right? Then I'm basically going to go back to what I've done before, where I'm actually going to be using this guy now. Okay, x start from 0 all the way to 5. So, which means from a joint, several questions can be asked. I can ask you, what is the expectation of x? What is the expectation of y? If you want to get expectation of x, you need to first get the p of, the distribution of x. If you want to find the expectation of y, you're also going to do the same. Now, take a look at that of y. You see p of y now? 0 to 2. Okay, and if I actually go back on how I got the 0 to 2, okay, if I want to go back, okay, I'm actually going to be focusing, okay, on this guy for y equal to 0, for y equal to 1, and for y equal to 2. Oh my God, there are 3 possibility under y. What I'm doing now is like I'm interested in y, and I'm actually summing over the range of x that I'm not interested in. Okay, so when you do that, you now have you got a guy now. I told you check. If the sum of the probability does not give 1, something is missing. Now, do you know, based on that, if they ask you to find the expected value of y, okay, if they ask you to find the expected value of y, all what you just need to do, okay, expected value of y now, okay, so all what you just need to do, summation y, p of y, okay, don't forget, y start from 0 to 2. Then you'll be able to find the expected value of y. Now, another question now is asking, take a look at number C. Okay. Yeah, when if you want to make sense of this particular data set, X represent the numbers of cars and Y represent the numbers of buses. Okay, per signal cycle at a traffic signal in a given, which is given by what you see. Now, if you take a look at C now, suppose a bus occupy 3 vehicle spaces. Oh, a bus occupy 3 vehicle spaces. A bus is very big, right? Okay, now, and a car occupy just one. Of course, a bus is bigger than a car. Now, what is the mean number of vehicle spaces occupied? Oh my God, the mean number of that spaces occupied. That is basically going to be a linear combination, okay, which is going to be x plus 3y. This is the x of x s of y that I was talking about the other time. I said that is not a probability function. I told you h of xy is not a probability function. But right now, we basically want to figure out about on the mean, the average. Okay, so if I want to figure out the average, it means I want to find the expectation of x plus 3y. The linear combination here involves two measurements at a time. The probability function that I'm actually going to use will not be marginal. It's going to be a joint probability function. Anytime you want to figure out the linear combination of x and y, then the probability function you need is a joint. Does that make sense now? Okay, so what I'm trying to say now is basically take a look at that. I want to find, I'm going to circle that now for you to be able to see. Okay, give me 1 second. Okay, I'm talking about this guy now. It's now going to be two summation because we got x and y. The linear combination they talk about is plus 3y multiply by the joint. Joint. What am I going to be doing now? I'm now going to consider possibility. Okay, the possibility. Okay, when next I'm going to be going back, the number of possibility I'm actually going to have. Okay, is you're going to go back to the table. That will be about 18. 3 levels of y, 6 level of x, 3 times 6. That will be 18. The very first thing I'm going to do, when x equal to 0, y equal to 0. Okay, when x equal to 0, y equal to 0, you're going to plug that into x plus 3y. That will be 0 plus 0, which is 0. Then what is the corresponding probability for that? Is 0.025, and that is the reason why you are actually having 0 as the first one. Then you're going to continue all the way. Okay, there's going to be 18 possibility. Does that make sense? At the end of the day, we got 4.90. Okay, and let me also tell you this. If you don't want to go that way, if you don't want to go that way, okay, because what you basically, what they ask you to find, what they ask you to find is the probability of x plus 3y. You can use method of linearity of expectation. This is the same thing as expected value of x plus 3 expected value of y. You can just find this using summation x p of x plus 3 summation y p of y. Y here start from 0 to 2 and x here start from 0 to 5. You see that? And whatever you get here, then you add them up. It's still going to give you the same results. Whichever way you want to go, the result is going to be the same. Okay. Now, I want to go into continuous case. The discrete case is kind of easy. But continuous case, because it involves calculus, and I'm going to advise that you revise your knowledge of calculus. For those of you who have lost some touch with calculus, please set up an appointment with me during my office hour, I can brush you through some basic fundamentals of calculus that you need in this course. Okay, now I want to go into continuous case. Now, okay, now we are still on a bivariate. What do I mean by bivariate? It means we're focusing on two measurements at a time. Bivariate. We can also have situation for more than two. When you have more than two, that is going to be called multivariate. Okay, the one we've been doing, like this guy now, just X univariate. Univariate. Okay, so that is the definition. Of course, you know f of x, y has to be non-negative. Of course, then the integral f of x ds y must also be equal to 1. Okay, the total space, the total area under a curve has to be that. Okay, which is basically, take a look at this. If I want to have a graph of x, comma, y, okay, and the joints, how many do I have? That's a three-dimensional space. X, y, and the joint distribution. Of course, this is what you're going to see. That's what you're going to see. Okay. Now, I quickly want to move now. I think I walked you through all this yesterday, but you know what? The same way that we find expectation of a linear combination in discrete, we can also find expectation of a linear combination in continuous when the probability function we are actually using is you know it's a joint. Okay, let's take a look at the first one. It's just trying to tell you the probability of xy lies in A. Okay, if I want to figure that out, I'm actually need to integrate a probability density function, which happens to be the f of xy, which is the joint distribution. And of course, the second one is trying to say, okay, I want to get the marginal. I have an f of x, I have f of xy. In the discrete case, we're summing, right, over the variable we're not interested in. In a continuous case, we're actually going to integrate the joint. For instance, I'm looking for f of x. Okay, I'm actually, talking about, if you take a look at this guy now, and you take a look at this guy now, those are called marginals. I'm looking for f of x. I have f of xy. Okay, I'm actually going to integrate the f of xy over the range of the variable I'm not interested in. I'm interested in x. Then the integration will be done with respect to y. If I'm interested in y, the integration will be done, okay, with respect to x. And the range of the integration is basically going to be the state space of the variable I'm not interested in. Okay, I want to go into number 3 now. How do I now find the mean of a linear combination if f of xy is continuous in nature? Okay, this is what I'm trying to say now. H of xy is a linear combination. It could be x plus 3y. It could be x squared plus 4, whatever. Okay, go ahead. That's a very good question. Somebody asked whether would that be provided as a question, or you just have to figure that out. Actually, that will be provided as a function, as a question. I'm going to give you what is your h of xy and what is your f of xy. Okay, the moment I give you the two, okay, how do you now find the mean? This is the formula. I'm showing you the formula now, right? I'm still going to show you an example on how to go about that. Okay, now we take a look at it, number 3 now. That's a mean of a linear combination. But when you take a look at number 4, okay, take a look at number 4. Oh my God, look at number 4 now. You're basically going to say that even though you are giving a joint and somebody asks you to figure out the conditional mean of x, the conditional mean of y, then you need to, for force, do number 2. Do you see number two? In number two, you need to first figure out your marginals. Let me tell you this. If your marginals are wrong, then whatever mean or variance or whatever statistical inference you want to compute from that will be very, very wrong. And that's why you need to be very, very careful. Okay, you need to be careful. Okay, now we're going to go into the next one now. Let's take a look at the example. I need everyone to focus the board. The example that I'm giving now, this is an equation that I used yesterday when I was talking about the proportion of customers, that use working facility in a bank and the proportion of customers that use driving facility. Of course, there are two alternative way, okay, to actually, make a transaction when you go to bank. It's either you drive in or you actually walk in. Okay. Now, if X, okay, represent the proportion of time, okay, the working facility is being used, and Y represent the proportion of time the drive-in facility is being used. Why do we have this function? Why do we have a joint here? We actually have a joint because the two events are taking place simultaneously. If you try and go to Wells Fargo now, or you go to Bank of America, you're basically going to see, the two events are going on simultaneously. And mathematicians, they've looked at the situation and they have that as a model. Okay. Now, why do I have a model? I have a model because we basically want to answer, a question, a practical question. Take a look at this practical question now. You know what this guy is talking about. What is the probability that the proportion of customers that are using drive-in, and at the same time, the proportion of customers using walk-in, that proportion is going to go from 0 to 25%. When I say 25%, it means, each facility is underutilized. You know what I mean by underutilized? Like under, okay, underutilized. That is not fully utilized, got 25% capacity. That's what we mean. So that is what that guy is saying. What is the probability? The proportion of time the working facility and the proportion of time the driving facility is used is just going to be go from 0 to 1/4. 1/4 is 25%. And what do we figure out? If I want to do that, I'm actually going to have two integrals. The first integral is going to be for the range of x. Second integral, range of y. Second integral, range of x. And you have to do, that's why you have the x, the y. You first do that of the x, okay, before you now do that of the y. In the end, getting this result, you know what I mean? If you basically want to explain this to manager of a bank or those who take decision in a bank, you need to multiply this by 100%, by 100. Now multiply 0.01, that would be like 1 point something percent. You know what happening? 1 point something percent. Okay, the probability, that probability is very, very small. 1% of a time is when you're going to have a situation where the proportion of time the two facility, okay, are being used, going from 0 to 25%. Is just 1%. 1% mean is very, very small. That doesn't mean it can't happen. It doesn't happen frequently. The bank actually need this information to take a decision. They don't want a situation where their customers, they're going to come and spend a lot of time. Okay, the customers, time is money. You get what I mean, right? Okay, now that's how you're going to do that. Now, please, I need you to pay attention to where we are now. I'm now moving from two variable situation to three variable situation. X1, X2, X3. And if you take a look at this, f of x1, x2, x3 equal to k into that. K is a constant. Okay. And you know what I want to do? I'm giving now this as an extra credit. K is 144. I need somebody to prove that. If you're able to prove that, send it to me for extra credit. You are using that function. okay, into x1. How many integrals are you going to have? How many integrals? Three integrals. Okay, take a look at that. Okay, and look at the range. Okay, look at the range of x1, xi. Xi lie between 0 and 1, mean x1 lie between 0 and 1, x2 lie between 0 and 1, x3 lie between 0 and 1. But there's another restriction. X1 plus x2 plus x3 must be less or equal to 1. Okay, you got to put into consideration that. But you know what? If I have x1, x2, x3, and look at the question A, compute the joint marginal density of x1 and x3 alone. Oh my God. You know what happened? Okay. I'm gonna oh, okay, let me do this. Now, what actually happened now, okay, is the fact that, take a look at this guy. Even though I have x1, x2, x3, but I'm not interested in all of them. I'm only interested in two. When I'm interested in two and not interested in all of them, that's a marginal. What am I just going to do? Then I'm going to integrate the function with the respect to the variable I'm not interested in. What am I interested in? I'm interested in x1, x3. Then integration will be done with the respect to x2. Take note. You're always going to integrate with the respect to the variable you are not interested in. Because when you do that and you now use the range for that variable, that is a way to what? To terminate that variable. You want the variable to vanish. When you do your mathematics very well, that is what you're going to get. And why is it that ds2 is 0 to 1 minus x1 s3? Not only ds2. If I want to, let's say for instance, I'm looking for f of x1, x2. If I'm looking for f of x1, x2, I will be integrating with respect to x3, right? The x3 is going to go from 0 to 1 minus x2 minus s2. S1 minus s2, because of the fact that, do you see the restriction? The restriction is x1 plus x2 plus s3 less than or equal to 1. Okay? Now, the next thing I'm going to do now, they can ask you to find the probability of x1 plus x3 less or equal to 0.5. But let me tell you this. You cannot answer question B without you, for force, obtain a function that has to do with x1 and s3. What you see in the linear combination for B is x1 plus x3, and what I basically need is f of x1, x3. And you've already obtained that from A. Look at it, you see that the function is what you obtain from A, f of x1, x3. That function, 72x1, 1 minus x3, 1 minus that, is what you're actually going to use now. Take a look at that. You see, that's what I plug in. Take a look at that. Now, x1 plus x3 less or equal to 0.5. If I want to do that, ds3 dx1, because I'm talking about x1, s3. The S3, what is the range for the DS3? The S3 go from 0 to 0.5 minus x1 because of the what? Because of that restriction. The first one, okay, if you take a look at the x1 now, we're going to go from 0 to 0.5. Integrate that, you get 0.53. Okay, now do you know that another question can be asked now? Obtain the f of x1. Of course, if I want to obtain the f of x1, I'm just going to go into I'm going to use the joint f of x1 x3, f of x1 x3. And I'm actually, that's why you say f of x1 x3. I'm interested in x1. I'm going to integrate that with respect to x3. Okay, so take a look at that. Okay, now from there, I want to quickly move to conditional probability. I showed you all this yesterday. Whether for discrete or for continuous, okay, that's what you're going to have. F of y given s is going to be the joint divided by that. So which means if you want to figure out the conditional, You basically need the marginal and the joint, okay, whether for discrete or for continuous. Now, uh, take a look at this. This is for discrete now. Okay, I've given you that is example that look like this before. I'm not going to spend my time on that, but you know what I want to do. What of if you are given a table like this, and the question they ask is a question of conditional probability? Look at it. Give it that s equal to 1. Determine the condition PMF of y. Oh, the values of x has been given. When the values of s is given, it is no longer a random variable. But the values of y is not given. Then the numbers of answers you're going to get depend on the state space of y. So why do you think what you want to find is this? Take a look at that. Okay, what does that tell you? The range of y is 0, 1, 2. You already know your x to be 1. They see that? You already know your x. They gave you to be 1. Therefore, the range of y is going from 0 to 2. And which is what you see here. Is that not? Look at the y. Is that y go from 0 to 2 in the table? You see that now? Okay. Now, uh, if I want to find, you now want to find p of 0 given 1. Look at the way you're going to work it out. P of 0 given 1 will mean the joint of when x equal to 1 and y equal to 0. Let's see. When s equal to 1, y equal to 0. When s equal to 1 here, and if you take a look at this, y0, x1, what is that probability? 0.08. You see that? That's a joint. That's what you're going to have in the numerator. Okay, so when you have that in the numerator, then the next thing now, you want what is the probability of x? Okay, so here now the probability of s is 0.34. For each of them, you're going to see the denominator is the same, because that is for x equal to 1. If you want to go back, the probability of s equal to 1 from the table here, if you want to figure out what is the probability of s equal to 1, what are you going to do? S equal to 1, right? You're going to add the 0.08 to 0.20 to 0.06. That is going to give you 0.34, okay, which is the denominator you've been using. Any question about that, A? That is what you're going to have. And the moment you have that one, look at another question. To obtain y given 2, y given 2 means you want to find the values of y when s equal to 2. Initially, we're focusing when s equal to 1. You do the same. We got this guy out. Okay? Now, in another question, look at question C. The probability of y less or equal to 1 given s equal to 2. Oh, given s equal to 2, s already known. But right now, I'm not going to use all the state space of y. Even though I know y go from 0 to 2, but it said y less or equal to 1. Oh my God, y less or equal to 1. I'm actually just going to consider 0, 1 for y. That was why you see 0 given 2, 1 given 2. Does that make sense? Okay, so then every other one goes, but you know what? Very easy when we are actually talking about discrete. But let's come to continuous. I needed to see this this particular example now. Let x and y, pressure for right and left tires, have density k into that. Of course, anytime you see a range like this, what does it mean? It's actually mean x line between 20 and 30, and y also lie between 20 and 30. Of course, because we expect the same pressure on the tires, right? Okay, now determine the conditional PDF of y given x and the conditional PDF of s given y. Okay, that is it. Okay, but before you can actually solve this problem, you need to first determine what is the value of your k. As I'm saying, k is a constant. Okay, you want to get the value of your k. When you integrate this over, 20 to 30. So if you want to show that, that's what I'm showing. But that's what I'm showing here. You can revisit. Oh, before I take this is if you basically want to show that. Okay, what you're going to do, integral 20 to 30, 20 to 30. Okay, k into x squared plus y squared dx. The y must be equal to 1. Then you need to solve for k. Okay, so you can try that. Okay, you need to solve for k. Okay, so solving for k, we actually give you, you're going to get a result for k. And the moment you get a result for k, of course, you're going to have your f of xy. And when you have your f of xy, you want to find a conditional. Look at that, f of y given s. F of y given s, you're going to be f of xy divided by f of x. But you need to first get your f of x. How are you going to get the f of s? F of s is going to be integral f of xy dy. Okay? You need to first obtain that. The range of y is still going to be 20 to 30. Okay? So now if you get your k very well, your k would be 3 over 380,000. Okay, you can try that. Now look at question B. Find the probability of y greater than or equal to 25, giving s equal to 22. Before you can actually figure out this guy, you need a conditional function. That is going to be conditional function of y given x. Because they said find the probability of y greater or equal to 25, giving s equal to 22. You need a conditional function. So the conditional function that you need is actually f of y given x. Okay. Now the f of y given x, you've already, so you're going to have a way to derive the f of y. Like if you want to get the f of y given s, okay, if you want to get the f of y, okay, the f of y given s, okay, the f of y, uh, the f of y given s equal f of xy divided by f of x. And you've already derived your f of x here. Okay, that is what you see here. Okay, that is exactly what you see here. Okay, and wherever you see x, you plug in 22. Okay, now you now want to integrate that by y. Why are you integrating by y? You are integrating by y because they said y greater than or equal to 25. You are focusing on y greater or equal to 25. That is going to start from 25 and stop at the highest value of y. What was the highest value of y? 30. That's why you see 25 to 30. Please take notes. Okay, at the end of the day, you get a 0.783. Now, if you now take a look at the other one here, now, do you know where I'm coming now is this? What is the difference between this guy and this guy? Okay, the very first one is a conditional y given x, but the second one is unconditional. Okay, you're going to see that we're focusing on, in the two, we're focusing on y greater or equal to 25 in the two, except that in the first one, okay, we are conditioning that on the values of x. Let me now tell you this. Situation where conditional probability equal to unconditional, then x and y are independent. Now, are they independent now? They are not, because the result that we got for that guy, okay, for this guy is this, and the result we got for this guy is that. Therefore, that's another way to show that x and y are not independent. They are not independent now because the conditional probability is not the same as conditional. Now, oh my God, do you know we can now find the conditional mean? When I started, I told you, okay, now here, what is the expected value of y given that s equal to 22? This is different from just expected value of y. Expected value of y is unconditional mean. But this guy now is a conditional mean. When I'm talking about conditional mean, I actually need a conditional function. What am I interested in? I'm interested in y. That's why you see integral y. Then I'm going to use a conditional function, f of y given s, because I'm talking about expectation of y given s. Take a look at that. Then I'm done. Then the moment, the same way that we normally find variance, when you are talking about the unconditional, if I have a unconditional mean, the unconditional variance is this, right? If I want to get the unconditional variance, what about for conditional? For conditional, if I find the expected value of s given y, okay, then the variance is going to be expectation of s squared given y minus the expected value of this or squared. Look at that. Okay, that's what you're seeing now. We've obtained the conditional mean to be that. And I want to obtain the conditional variance. I need to first find expected value of y squared given s equal to that. From there, I'll be able to get my variance. Is there any question on that? Okay. So please go back to your calculus. Okay. This the bivariate normal distribution. This is in the next material, the material for tomorrow. I'm not going to discuss about this now. Okay. Leaving that one for tomorrow. And I put some exercise here. More example on the discrete. Can you see that? This is a more example on the discrete. And I'm going to talk about this briefly before I go. Suppose the joint distribution of x and y is that, okay, how can we show that that x and y are independent? You know what you're going to do? Obtain the f of x. Obtain the f of y. If you multiply f of x by f of y, if we give you f of xy, then they are independent. Otherwise, they are not. Okay, that was what I show. Look at example 9 now. Example 9 says find the marginal density of f of x and f of y. That's super easy, right? You have a joint. You can get the f of x by integrating f of sy with respect to y using the range of y. You get the f of y by integrating the joint with respect to s using the range of x. And check if the variable s and y are independent. If you multiply your marginals, f of x and f of y, if it give you the joint, then they are independent. Then you can compute that guy. Okay, I think I put something here, which is what I've already explained to you before. Take a look at all of that. That's super easy. Any question before I go? I've already uploaded midterm practice question this time around. No, there is no multiple choice. Okay, but I'm going to give you more clue about the area, the midterm too. We cover tomorrow in class. Okay, I need you to attend my class, the punctual tomorrow. I'm going to give you a lot of information about the areas, the midterm too we cover. But what is very, very crucial, assignment solutions. And that was why I instructed my TA to post assignment solutions. Okay, make sure you go through those assignment solutions and the practice question for last week. I know my TA walked you through some questions in the lab last week. Very important too. But tomorrow I'll give you more information about what the expectation is going to be. This time around, no multiple choice. They're all going to be short answer question. Does that make sense? Okay. And I think I'll give you more information tomorrow. And this time around, the exam is still going to be between 14 and 15, except that you're going to log on to the Zoom with your video on. Whenever you want to do it, within the window. I'm not even if I'm not online, there's no problem. It will be recorded automatically. Okay, it's going to go between 14 and 15, where the moment you start, your time is going to be running out. But more information about that tomorrow. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.